Okay, so we're going to continue on with transport of reactive compounds. So our sodium chloride is what's considered a non-reactive transport, a conservative tracer. It moves with the water. And so we're going to look at things that are dissolved, so constituents that are dissolved inside of water, contaminants that are inside dissolved in there. We've already kind of talked about this. So we talked about absorption. So, that's adsorption and absorption. That's where, it's either stuck onto the outside or gets into it. So we call it absorption as a total thing. But it also can mean cation exchange capacity. So what is cation exchange capacity? Well, you've got your clay particles, and they're generally are negatively charged at normal groundwater pHs. And when you have a net negative charge onto there, all your positive cations will stick to it. Well, normally inside of soils, you'll find sodium, you'll find calcium. These are pretty normal. But what happens if you have like cesium inside of there, that it's a contaminant of choice? Well, the cesium will exchange with the sodium, will exchange with the calcium, and then it'll release the sodium out into the environment, allowing the cesium to attract onto there. So these are weakly bounded negative charge like surfaces, and this will cause retardation of the cesium because it's going to be exchanging on and off of calcium to the net negative charge of the clay particles in the cation exchange capacity. There's also phase partitioning, and this is where the TCE prefers to be inside of the solid molecule. It is hydrophobic. And so we have organic molecules that don't like to be in the water phase, so they want to be in the solid phase. And so if there's any sort of like organics on top of the soil, so any of that kind of stuff would cause the contaminants to stick onto the soil and stuff. And all these processes are fast and reversible. So we've talked a lot about these. So what's new and what we're going to really kind of focus on is how do we test for these things, some of the processes that go into this and everything else. Well, one of the things that we use is what's called a batch test. A batch test is used to measure the influence of absorption for a given contaminant in soil. So how do we do this? So batch tests, we call these, we also refer to them as isotherms. So you'll hear that term. But a batch test is just where we're taking a vial. We add some soil. So this is our soil in here. We've got our water plus our contaminant of choice in there, and so we want to see how long this absorption takes. So the sample is mixed and allowed to equilibrate. Oh, I always have problems with that word. And the concentrations are measured in the water. So so the contaminants are inside of this water system here. And then as we're mixing these things up, and usually we'll do this after like 24 hours. So these things will be on like a shaker or I have a thing that kind of rotates around. And then what we do is we'll centrifuge it, so it'll pull all the sediment to the bottom, and then we measure the contaminant that's still left inside of the water. So fairly easy allowed to do there. We can repeat this over, and we can do this over a wide range of contamination concentration. These are relatively small. We're just looking at the soil inside of there. So we could repeat this over and over again with a large number of different contaminants. So what we'll end up doing is we'll have the concentration in the solution versus the mass of the contaminant. I'm not really great at writing on the side, so mass of the contaminant sorbed to solids on this axis per unit mass of solids. Okay. So we have the concentration in the solution, and then we have the mass of the contaminant sorbed to the solid per unit mass. And so when we do this, we end up with so we do different concentrations, and then we will draw a linear line through it, and the slope of that line becomes our KD. Our KD is our distribution coefficient. And it's the slope of the line. So this is it. So, this is how we'll test for it. Well, these things, this is only valid if, this has to be fast. It has to be reversible. Things that we talked about over here. It has to be fast. It has to be reversible. In there, there's unlimited potential. So it doesn't really matter how much concentration of solute you put in, which, doesn't really happen and stuff like that, especially when you start getting into some of these cation exchange capacities. You can overwhelm the system. So, but, it works at low concentrations. This works best at low concentrations. It works best into there. And so you'll get a linear line. Now, sometimes when you get into this, part of it will be linear and part of it won't be. And what will happen sometimes is you'll have your linear part here, and then it'll start to flatten off, and it'll do this. And we only use this linear part to develop our KD, and we leave this part alone. Now, I have done things where there's multiple absorption KDs, where you can actually get like where it's linear here, then it changes and it gets linear. Like you can have this linear, and then this linear, and depending on the concentrations you're at, the curve can look different in different areas. And so you can have KD at very low concentrations, middle concentrations, and high concentrations be completely different. And so that is completely possible to have happen in your system. Okay, so what influence does this have? See, I spent a little time drawing, making it look nice and pretty instead of my normal hatchet jobs inside on here. So we can drop this down here. So this is D2. Okay, so what is the influence of absorption on advection? We've touched upon this about advection transport. So if absorption is fast and reversible, it retards the transport relative to the average flow velocity. So if this over here is the solute with, so this, pretend like this is the solute with no absorption. So it moves much further inside of this. So this we can say is distance from a source at time t. So it moves farther along because it's moving further along. And then this, the green one, is the solute species with absorption. Okay, so it doesn't move as far along inside of our system. So D1 equals the distance traveled at C over C naught equals 0.5 for non-sorbing things. So the velocity of the groundwater times the time elapsed, so that's V over T, will equal the hydraulic conductivity divided by the effective porosity, change in the head over the change in length times time. Okay? So for D2, so this thing that is absorbed onto here, we get the distance traveled by absorbed solute. So that equals the velocity of the retarded solute times time equals velocity t, velocity of r times t. So we get a retardation factor. So this is our capital R, which equals our retardation factor equals V divided by VR, and R has to be greater than equal to 1. So if it's equal to 1, then it's not retarded, then it's this one over here, the purple line. But if it's greater than 1, then it's retarded, and the numbers inside of there make some predictions. So theoretically, R can be related to KD. Okay, so our R down here, our retardation factor is related to DKD, our coefficient, our distribution coefficient. So R, our retardation factor, equals 1 plus the bulk density of the soil. So that's that, divided by the effect, the total porosity times Kd. So if we know our Kd, which we just talked about in our last thing, we know what the bulk density of the soil, which we can measure, and a lot of times we can look those things up. A lot of soil scientists do those. We know what the porosity is. Again, we can assume it's 0.3, but we can also measure that. We can measure Kd in the laboratory. We can figure out the retardation of a contaminant based upon some basic soil properties. Things that we can measure inside of the lab, we can come up with a retardation factor of the system. So if you measure Kd, the distribution coefficient, which we already talked about, you can estimate the degree of retardation of a solute in any soil. So this is what you can do. You can bake these estimates on there. So we can go into there and we can get some examples here. So we can go like, here's some solutes. Here's a soil type that we're looking at. Our Kd, which has units of milliliter per gram. And then we can get our R value. So let's look at scrontium, 85. Let's look at it in a bentonitic clay soil. We figured out the Kd to be 21, so our retardation factor will be 11. Let's look at PCE. Let's look at it as sand, like the Borden sand, which we've talked about there. The Kd was only 0.4, so our retardation factor is 3.6. So Kd can vary anywhere, can vary from 0 to about 1,000 milliliters per gram. But for values greater than 10 milligrams per gram, the solute has very low mobility. So if the Kd is greater than 10 milliliters per gram, then it's so slow. It's very low mobility in groundwater. Okay, so PCBs. So polychlorinated biphenyls, if you should be able to draw those, and dioxins. Now we didn't talk about dioxins, you should look those up. Those are major contaminants, have very high Kds, and are rarely distributed in groundwater. Okay, so we don't usually find those. So if we know the Kd of a system, and you can look these up, you can detect it. So Kd varies due to heterogeneities. So the problem here is, if you notice, we had to talk about the soil type. Now, if I put PCBs with a clay, it would have a different one. If we put it with different soil types, it's going to affect the Kd. So you have to do this for that particular soil type or that location. It interferes with other solutes, and when we talk about these tests that we talked about here, these batch tests, usually we do one contaminant at a time. We don't do interfering contaminants. And so we'll talk about Renault and some of the other issues with that later on. It's inaccurate at very, very low concentrations. And so there are some major issues with this when it comes to the system. So the transport of reactive solutes. So when we're looking at these systems, and so when we look at it, so we have the one-dimensional advection dispersion equation with our absorption and with our retardation. So we look at the advection dispersion equation for transport in a porous media. The change in the concentration with change in time equals dl over concentration x plus change in concentration, okay, minus the bulk density over the porosity, the volumetric that's the volumetric moisture content, change in concentration over change in time, plus the change in the concentration to the change in time reaction. So this part here, this is dispersion. This part here is we are, sorry, this should be a negative. So this is our advection. This is our absorption. And then this is loss or gain. So it could be a positive or a negative sign here. Anything that is not absorbed. So if you remember, DL is our hydrodynamic dispersion coefficient. So this is the Bx plus D star. So this is our dispersivity, and then this is our effective diffusion coefficient. This is our average groundwater velocity. This is bulk density. This is volumetric water content. And so we assume this equals porosity. So we assume that the whole system, so we assume theta equals our effective porosity in a saturated system. So this is porosity. This right here is our constitute of the sorbed per weight of soil and time, and then this is just the constitute in there. So what we're doing here is we can see that if you have advection, the system disperses. We can get them sticking onto the system, which will retard it, and then we can lose or gain it, and that'll move the curve up or down, or we can start losing the system inside of there. So absorption processes that we've talked about here, they're reversible, so they can move the thing, transfer the solute mass between the groundwater and the soil and the aquifer material. So it's slowing it down, and it may stick really hard, so it depends on the system. Often assumed absorption and desorption are fast processes, so that they are always in equilibrium. So it's an equilibrium process. Fast reversible absorption of a solute causes its movement to be retarded compared to the average groundwater velocity, so like a salt solution or something like that. And the simple sorption models are often used to describe behavior of dissolved inorganic compounds, metal, arsenic, things like that, and some of our organic compounds that we talked about. However, many contaminants do not fit into this very simple sorption, advection, dispersion equation here, especially at high concentrations. And so when we start reading some of the papers or we're going into things, that's when we start really seeing some variations inside of there.